I'm Mike Butters. I'm Vice President of Signal Technologies for Nativis, a biotech company located out of Seattle. Was out of San Diego until just shortly. Our work involves studying the electromagnetic interface between a drug and its receptor and trying to understand more about what actually is occurring there. To begin the discussion, I would like to move to a bit of an analogy. The Hubble Space Telescope was launched approximately 25 years ago or so, and there were a tremendous amount of images that were produced of stars and galaxies and other objects deep in space, clear to the edges of what we are able to observe within the universe. But astronomers began to wonder what would happen if they were to train the Hubble telescope on a section of the sky which was not believed to contain anything. There shouldn't have been any information, no stars, no galaxies. It should have been a piece of blank sky. So they did, and they let the telescope soak in light for a period of time, and then they began to analyze the result. The result shocked everyone. In an area of the sky where there shouldn't have been anything, what they found were thousands of galaxies, not stars, not individual stars, but entire galaxies that basically covered the entire image. Nativis has done something that is somewhat similar to this, and this is the analogy portion. We have developed a device that instead of looking outward as a telescope would, we are looking inward. We're looking at the electromagnetic environment surrounding a solvated chemistry in solution, and particularly in a dipole solution. So we're also looking in an area that has been pretty much understood up until recently, that it really doesn't contain a whole lot of information. There shouldn't be a lot of spectral content there. But we developed a device that would allow us to look at that area. And what we found was equally staggering. We found a tremendous amount of information that was present within the spectral analysis of a solvated chemistry at extremely low frequencies. Molecular modeling up to date has been fairly limited in its ability to look at the dynamics of a system and oscillations that were associated with those dynamics. By running calculations over a few milliseconds, they were able to produce predicted spectra that ran down into the tens of kilohertz, 40 kilohertz, 60 kilohertz, and so forth. They believed that they would be able to find spectra that was of a much greater wavelength than that, things that were approaching down towards DC, obviously not at DC, but approaching it. But those models would have to be run over a particularly long period of time on the largest distributed processors that were available. And so to date, no one has really done it longer than those few milliseconds. Science is also limited in its ability to measure solvated chemistries in solution. The techniques that are used right now will either cause some sort of they will perturb the system in some way. They will heat it, or there's a common method for looking at solvated chemistries in thin films, where you have an interface, an interfacial surface that limits or totally excludes the ability to look at a system in bulk water. And in order to really look at a system within nature and find out what is occurring dynamically within a system, you need to be able to look at that system in its native state. When we do this, when we begin to look at a solvated chemistry in bulk water, or even to look at other dynamics within a molecular system, the oscillations are nonlinear and they are also difficult to characterize. So when we try to find the information that is available within the solvated chemistry in the dipole solution, what are we going to look for? We're going to look for magnetic environments that may surround these chemistries. We know that, for instance, that there are moving electric charges that produce magnetic fields. These do exist in solvated chemistries, both inside and inside the solvation shell, and also depending on the chemistry itself. We know that changing electric fields produce magnetic fields through Maxwell's correction. And we also know that electric dipoles, such as a water molecule, although it has poles that should cancel each other out, it should have no net charge. If the two poles are close enough together, there's a current that actually develops between those two poles, and orthogonal or perpendicular to that electric field exists a magnetic field. So how big are these fields? Well, they're very, very tiny. They're small. Ordinarily, when you think about the charge state of an atom or a molecule, you're generally thinking in the terms of whole electron volts. In this particular case, we're looking at very tiny fractions of electron volts. 1 to 10 to the minus 13 electron volts, 10 to the minus 19, 10 to the minus 32 joules, which actually is a corollary to the electron voltage. But for practical purposes, with the instruments that we're using, which are squid-based magnetometers, we're looking at the 4 to 100 femtotesla range. Now, even with this range, with the very exquisite instruments that we're using to measure these fields, they're still not sensitive enough in most instances to actually detect these really, really tiny magnetic fields. So how do we measure the field? We use a superconducting quantum interference device, which is a low-temperature helium-cooled device that has a theoretical sensitivity of approximately 4 femtotesla. Some of the more recent squid devices are getting down to around 1 femtotesla. We also couple that with a second derivative gradiometer, which those folks that understand NMRs and how they're put together understand that there are 4 coils within that system. Traditionally, within an NMR system, the coils are configured positive, negative, positive, negative. They're all in series. The sample is placed in one of the coil sets. That samples the area surrounding the target of interest, and the other coil set basically samples the environment. And the environment is subtracted from the target sample, and you end up with an improved signal-to-noise ratio for the target of interest. We do pretty much the same thing, with the exception that we add something else. We add stochastic resonance. So the system that we operate has a noise injection that is orthogonal to the gradiometer in this type of a configuration. On the left, you can see the gradiometer. You can see the orientation of the coils. A little bit different from a conventional system you would see with NMR. We actually place the sample between the middle 2 coils, and those coils are running together in parallel with one another. The 2 outer coils are running in opposition, and the entire system is set up to operate in series. So we get an effective reduction at about 1 kilohertz of 60 dB just within this setup itself. Now, this is inductively coupled to a DC squid device, which is then inductively coupled to the signal conditioners, which take the information and then we store it digitally. It can be stored as just about anything that you'd like, depending on how it's going to be used. For our particular purposes, because we're dealing with integers, a standard wave file is perfectly acceptable for both recording the data and storing it. The system is also further isolated from the outside environment with superconducting mu shielding. It also has niobium shielding, and just for extra safe measure, we have a superconducting lead bag that surrounds the whole thing. So about the only thing that we're really seeing inside that field around the target that may not be from the target itself are going to be some small eddy currents, and we have some ways of managing that as well. So stochastic resonance and the application of noise to the system is really important in being able to get the sensitivity of the system down low enough to actually detect the signals that we're really interested in. And it's not so much that we're actually diving in sensitivity. The truth is we're actually improving the signal-to-noise ratio of the output signal by adding additional noise. It sounds counterintuitive. It actually works quite well. The graph or the descriptor on the left shows two energy wells. We're simply bumping a system from a lower energy state into a higher energy state by adding a uniform noise over the top of the system. And on the right-hand side, at the very bottom, you'll see the little curvy line. Let's see if I can get, yeah, here we go. Little curvy line right here. Overlaid on top of that is we have some noise. The line just above that represents the detection threshold of the instrument. And as you can see that what used to be a subthreshold signal now has components that rise above the detection threshold. And the little image above that right here is an indication of the type of data then that we're going to receive out of that system. This system actually works quite well in lots of different formats. It's used in telecommunications, satellite communications. Anytime where you have a weak signal that's really buried in noise, you can actually add more noise to the system and improve the signal-to-noise ratio. Who would have known? This is an example of stochastic resonance in action. This is a taxane, happened to be paclitaxel, I believe, that we were looking at here. What you see on the screen represents 1,200 individual measurements of paclitaxel over several days. What we were doing was we were increasing the amount of noise that we were applying to the system for a couple of reasons. But we were applying noise at different intensities, looking for the production of a stochastic event. And as we continued to increase the amount of noise that we were applying, we indeed found that there was an enhancement of the signal-to-noise ratio where it's listed there at the first event, which was a noise field of approximately 50 femtotesla. So we're applying a very, very tiny field to a system, and we're getting a stochastic response from that. And the frequencies that we're using are extremely low. We're talking about a few kilohertz in bandwidth that is just above DC. As we continue to apply noise, we end up with a second event. And the second event is important because this is where we're taking a majority of our information. And we'll be looking at some of the data that we were able to produce from that here in a moment. As we continue to apply noise, we don't see a whole lot of things happening until we actually begin to overwhelm the system, and now we're pushing the noise above the noise floor of the instrumentation, and the signal-to-noise ratio begins to plummet. Another interesting side note on this is that these plots are developed using autocorrelations and Fourier transforms, and we're looking at power. We're essentially looking for how is power being distributed. Well, you can also use this as an indirect measurement of entropy. So as we're applying noise, again, in a counterintuitive sense, the more noise that we're applying at particular points, the less entropy is in the system. Then at where it says the noise floor is exceeded, we can obviously see that entropy suddenly increases and just continues to increase with the increase of the amount of noise that we're adding to the system. So the other thing is that we're looking at a non-linear modulation. We're looking at at proteins or other chemistries that may be wiggling and jiggling and so forth through Brownian motion in ways that really don't have any linear components. But we're really limited in our ability to analyze these without going into some types of nonlinear analysis that really won't tell us much about what signal components may lie within the time series records that we're producing. So I use here as an example a figure 8. The figure 8 might have something that's racing around it in that figure 8 pattern. And as it races around, if you were to look at a Fourier transform of that activity, you would see something resembling what I have to the right of that figure 8, where you have 5 spectral components. Those components are related to the frequency of this system, the dynamics, for instance, of that particular system. So there are 5 nice components. You know, at the zero crossing in the middle, we have the piece we have the spectral component in the center, and on either end we have the points where this object is basically reversing course. So, you know, nice representation for your representation of a figure 8. Well, now imagine that we take that figure 8 and we throw it in the air so that it has additional ranges of motion available to it. So it's tumbling and falling through 3-dimensional space. And if we were to take a Fourier example of that, we would see something that looks like what I have to the right below the 5-point example. Now, if you look at that initially, you would think, well, there's not a whole lot in common between the figure 8, the static figure 8, and the figure 8 that is falling and floating through 3-dimensional space. But if you look more closely at it, you find that all of the components that are present in the figure 8 are also present. And I have them marked by the red arrows. But in addition to that, there are some additional components that represent the oscillations that have been added through these additional freedoms of motion. In the real world, if you were to look at this type of a model, this type of dynamic system, the red arrows, the spectral components that are represented by the red arrows would also shift very slightly depending on the speed and the distance that something was moving either towards or away from the sensor. So, so within a particular level of reason, this is a fairly accurate depiction of what a modulation would look like in its static sense, and what a modulation would probably look like within a real world context. If you're looking at a molecule, or in our particular case, something that was solvated in a solution. So we take all of that information. We've now used the SQUID to look at a nonlinear system, and we need to analyze this data. We need to get some constructive result from that. So first of all, we're looking at a nonlinear system. We're looking at modulation. So that's going to limit the tools that you have available to do the analysis. We use autocorrelations quite a bit. The reason that we use an autocorrelation is because the autocorrelations are not only good at looking at linear systems, but they also are quite suitable in many instances at looking at nonlinear systems. And then you can take the autocorrelated time series, if you're doing the correlation in the time series, you can take the autocorrelated time series and then render that into the frequency domain through a Fourier transform. We also do cross-spectral correlations. For instance, if we take the measurement of 2 taxanes and we compare those directly through a cross-spectral correlation, we can see spectral components through a Fourier transform that are related to both of those signals. And of course, then we'll use Fourier transforms oftentimes as more a quality control issue to make sure that the signals that we have are pristine. There aren't any unusual artifacts or so forth present. We also use wavelets, eigenanalysis, and bin histogram analysis to look at data. Now, we want to know where within this bandwidth does the does our information reside? This is actually of a taxane. This was produced using eigenanalysis, using eigenvectors. Eigenvectors are really great at looking at envelopes or looking at spectral components. They're not so great at looking at power. But it told us specifically where the information resided. That envelope, the information is within that envelope. And as you see, it falls off after about 7 kilohertz or so. So with correlations, when we're looking at the data, we'll do autocorrelations of 2 signals. We'll also take background samples without a sample in the detector, so that we're going to remove any outside interference from our target sample. We'll do that by cross-correlating both the target information and the background information, subtract one from the other, and it gives us fairly pristine data. So this is an example of the data that we would see. The first, the top is taxane 1. It actually represents 2 signals taken at different times and cross-correlated, and with a cross-correlated background removed from it. So this is background subtracted. The second one is a taxane 2. This one happened to be recorded several days later. And we ended up with components that look very similar. So just to make sure that we're not fooling ourselves, we correlate across the 2 of them, and we can see data that is, some of the data is quite prominent. We can also see that there are elements of a noise floor there. We can look for statistical significance a number of different ways. One of them is you can look at correlation coefficients, which is actually represented on the y-axis on all of these plots. We can also look at the RMS, and we can do some multiples and do some thresholding by going, say, 10 times the RMS. And there is literature that describes some very robust techniques for looking at significance across certain bandwidths and so forth. So conclusions: the dynamics of solvated systems perturb the surrounding magnetic environment. Broadband perturbations are measurable using squid magnetometers, and perturbed fields contain information about the solvated system. So the implications to biochemistry are these. In informatics, for example, with RNA and DNA, we're looking at information that is specific to an RNA. We're able to look at the specific spectra. We have some other uses for that information. Diagnostics, we can compare the spectral result from two samples. We can tell you whether it's the same sample, whether it's the same material. We can look at dilutions and so forth. And if you have an analog, and you have measured an analog, and you have identified spectral components with an active analog, something that's bioactive, and then you have looked at other analogs who are non-active, non-bioactive, and have identified spectral content that is missing from that, then perhaps you have a drug discovery tool. Again, we have looked at this kind of in the same context that the astronomers had used in aiming the Hubble telescope. And I'd like to leave you with a thought that molecular information resides throughout the electromagnetic spectrum, not simply at the high end, not the high energy end, not simply at those areas above near infrared. And that low-frequency information is available, is both diagnostic and useful. That is my presentation, and if there are any questions, I'd be very happy to answer them.